That's right. Ah, thank you, voice of God. We are here. So let's go ahead and get started. And we're going to start with an easy one, an easy one. And don't say, Mr. Shelton, we can't see it. I know you can't see it. I'm drawing the picture ahead of time because people in the other classes were snickering at me when I was doing my drawings. And it's making me self-conscious and making my anxiety go up. And I was really sad. You want to laugh too? I'll let you laugh at the product. You can't laugh in the middle. Can I help you? Okay, just set it down, please. Thank you. So I'm gonna start. Oh, you guys still can't see it, right? Yeah, awesome. That's the way of things. Who the hell was that? No one's supposed to be coming to the door. He touched everything. It's bad enough that all of you are touching. Now people from the outside are touching things. He did. He touched everything. He touched the table. He touched the sign. He touched the door. He touched the plastic, and he touched the sanitation station. Didn't you see him? And then he put his arm on the other side of the plastic. I mean, come on. I have no idea. I'm not going to look in that envelope. Doesn't matter what it is. It's not to be good. I don't have to touch it. It's the mat. No, I'm not touching it. It's to Matt. It's yours. Here, everybody can watch Matt get the hazmat envelope. He's coming for it. Just the envelope. Don't touch anything else. He touched the table. You were supposed to touch the envelope and slide it to the floor. Oh, come on, people at home. Don't give us the bored look. Okay. The people at home are giving me the bored look. Look, people at home. I'm looking right at, I'm looking right at you now, but I'm actually looking at the computer screen where I'm seeing your faces. I got to tell you something that is true, and I'm recording this. So I know this is true because I'm willing to put it out on the internet. Ready? Everybody who's at school thinks that the people at home are at home because they're cheating or they want to cheat. I had a I listen to me carefully, had a heart-to-heart discussion about this in the middle of my research period on Wednesday when nobody was here, but then people came, which I still don't understand and it still bothers me. And they said in our discussion that they believe I'm sorry, I'm being interrupted by Matt Krotz. Hold on. Guys, what's going on? What are you? Okay, class. Matt is a Hispanic scholar from College Board. Are you Hispanic?
My mom's Hispanic.
Okay. So what's so funny? The fact that you are like a total white boy?
Out of nowhere.
I mean, I'm not saying Matt's the whitest person I know, but have you seen him at the beach? Looks like he burst into flames. Okay, back to physics. No, we're not. Because the people at home are bored. They got their bored face on.
Are they bored because you're not?
No. Now look, I have run actual statistics now. I was telling the folks in third period this. I've run statistics on our tests. The people at home are doing just as crappy as the people at school. So they're clearly not doing a lot of cheating. I mean, that's not everybody, but there's an equal number of crappy students at home and crappy students at school. So I see no statistical advantage to being at home except that you don't have to talk through a mask. And trust me, there are some definite benefits. I've got this sore right here on the top of the bridge of my nose. Every day, I put a little bit of ointment on when I get home. A little bit of that, a little bit like oh, it feels so nice, ointment stuff. So,
Most
all right, there it is.
teachers don't hear us. When we unmute ourselves, most teachers won't hear us.
But why? I want to hear you. I miss you guys.
No, most teachers don't hear us. Like, we'll talk and, like, keep on saying, like, hello, 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 and there's no answer.
Is that really happening?
Yes.
Okay, you should expect more from your teachers. Look, I worked hard to make all this. You guys have no idea how much I practiced to make this work. I do have the best setup. Well, I'm sorry. Look, Get it out. I want to hear all the things you wanted to say all day but couldn't. We're all ready for you. Oh, now you got nothing to say. Okay, people at home, listen, we're going to do better. We're going to find a better way to do stuff, okay? We're going to make this amazing. These are the sultry sounds of the Shelton voice, piped directly into you at home. All right, enough of that. There, we had a secret conversation. Yeah, I was doing my best impression of Barry White. Didn't really work out. Okay, let's go back to physics. Let's do this. There's a roller coaster car. Yay, the roller coaster car. I love roller coaster problems. I feel bad that I don't think there's going to be Busch Gardens Physics Day for the first time in 16 years. Well, you can go. I'm not allowed. But the car has a velocity V, roller coaster R. Here's what I want. What is the slowest speed that the car could traverse the loop? The slowest safe speed, assuming that the track can't pull up on the cars. It's a big assumption, I know, but that's what I want from you guys. I want to know, what is the slowest that the cars can safely traverse the track? Now, this should be a pretty straightforward question to anybody who was in my class last year, because we did it. And we're super smart. But, you know, you could use what you learned yesterday and solve this problem. I'm not given like more than 60 seconds for this.
Is it a smooth track?
Actually, that won't really affect the problem. But if you want it to be smooth, sure. No one wants to ride a bumpy roller coaster. They got rid of Gwazi for that reason. Yeah, it's a metal roller coaster. That sucker looks scary. I'm looking forward to, you know, someday when somebody invents the full body condom, you know, we're going to walk around the city again. All right, that's all the time you get. That was 37 seconds. Because I hope all of you recognize you're going to start with net force equals MA, and that's got to be MAC. Right? It's traveling in a circular path. There has to be unbalanced force for it to travel in that path. That shouldn't be a surprise. The whole unit is on centripetal acceleration. I expect to see the whole centripetal thing show up once in a while. But here's the big thing. We can't change the nature of the forces that we're using. Meaning, you're going to draw a weight. There's got to be a weight. It's got to be downwards. By definition, that has to be the case. And next, if there's another force, it's a normal force for sure, because we're in contact with the track. And based on where the car is relative to the track, that force has to be downwards. Now, these two forces can act to keep the roller coaster traveling in a circle. That's for sure. And although somebody brought up, what if it's a rough track? If there was a frictional force, it would be acting probably this way. But that still wouldn't change that to be at this point in the roller coaster, there is a minimum velocity. All that really means is that I'd probably have to be traveling even faster to get to that point, to overcome all that friction so that I can be going fast enough when I make it there. That's what that really means. And when I put all this together, look, those two forces act downwards towards the center of rotation. This should not be too big a deal. N plus mg equals, and now I hope at this point you guys are recognizing that all we do to make this different is put into v squared over r. But here's where you have to start asking yourself questions. This is where it becomes harder. Because when I look at this, and here's, if you really want to understand this, if you want to go beyond just, okay, I plug this in, I set this equal, if you want to be able to answer the questions, you know, the parts of the test where they don't let you put in any diagrams, like last year, when all you could do is type your response. This condition doesn't have to be met. You guys think that this is an equal sign as if it's an equation, and you got to stop thinking like that. If I want to go in the circle, I must have this much acceleration. I must have that to go in a circle. Now let's see what I have to work with. What I have to work with is this. That's what makes me go in a circle. So if there's enough, then yes, I go in a circle. If this side isn't enough, then I'm not going in that circle. It's that simple. So when I think of it that way, that this is how much I have to have, and this is what I have to work with, one of these doesn't change, right? This is what I have to have, At the same time, when I look at the forces, of the two forces, one of those I can't change. This is it. That one's going to stay the same. I can't really manipulate that. I'm saying that because we know that the normal force can change. It is a reactive force. It's a responsive force. It responds to the conditions in which it's been placed. But what it can't do is it can't be negative. It can't pull upwards on the cars. It can only push downwards on the cars. So I reach a inflection point, a point where I'm going from it being positive to it being negative. That is going to be the least amount of force that I can have in this problem when the normal force goes to zero. It's at that moment that that's it. That's the minimum velocity. Now, you would never actually build a roller coaster like this. Never. People do not like the way that feels. Not even a little bit. They get all squirrely. You start making them feel that way. If you were on a roller coaster and you lost contact with the seat at the top of the loop, you would never ride that roller coaster again. You don't want to come up against the harness. How many of you really love riding the Phoenix? You guys know what I'm talking about? Yeah, I don't see a whole lot of hands going up year by year. Nobody really likes coming up against the harnesses on the Phoenix because that's what the Phoenix does. It takes you up to the top and has you travel across the top slower than what it would take to actually be naturally traveling through that loop so that the straps have to pull up on you. Well, and the ball crusher has to pull up on you too. You guys know what I'm talking about? Yeah, I know. If you guys don't know what I'm talking about, you've never been on the Phoenix. If you've been on the Phoenix, you know exactly what I'm talking about. When they apply the pressure and then it backs off just a little bit, but not quite enough. Yeah. Yeah, I haven't been on the Phoenix. Is the Phoenix even operating anymore? I don't know. I won't ride it anymore. I've decided I don't need that in my life any longer. So now, how many of you have ridden Scorpion and did the trick I told you guys about last year? You guys know the trick I'm talking about? Hold the coin. That's right. You put the coin in your hand. I'll wait. Remember, this is the Shelton Show. They're all talking. You guys do know when I look over this way, I'm looking at you guys. Because you're not talking. We know when you're talking. The whole room knows it. And you just said you never get a chance to talk, but we hear you. We hear the pleas of those at home. You put the coin in your hand. You put it underneath. You don't put it outside because the wind will blow right out of your hand. You put it underneath, like on your knee, and ride the Scorpion. It'll stay right there in your hand the whole time after the lift hill. You have to get up to the top of the lift hill. But it stays there until they hit the brakes, and then it goes flying and hits the guy in the head in front of you. But the thing I want to point out is, even at the top of the loop, it's in your hand. Because in the Scorpion, and this is what's interesting about it, you feel most of your weight at the top of the loop. I want you to think of what that means. How fast must the Scorpion be going for you to feel your weight at the top of the loop? He asked, wanting an answer. I'll wait 60 seconds. People at home, 60 seconds. How fast must you be going for you to feel your weight at the top of the loop? The answer is right in front of us. 37 seconds left. Hurry, people. Hurry. I see it, Jackson. But I think the people at home are desperate to be heard. Desperate. They're tired of saying hello, hello, and not being heard. They're going to be heard today. 17 seconds. That's the end of the time. So let's see. Jason, where would I begin here? Do you know?
Not 100% sure.
Can you give me maybe an idea?
Could you start from one part before from the mg equals mv squared minimum.
I need to start one step before that, right there.
Okay.
So I said that we want to be able to feel our weight. And the thing about this is that we don't actually feel our weight. Like I've said before, and you may not have this in your notes, but I would encourage you to maybe get it there, is that we don't feel our weight. We can't feel the force of gravity. We feel normal forces because those are the ones that are in contact with us. If I was just to toss you guys off a cliff, you wouldn't feel that force pulling you down. You'd experience acceleration, sure, but you wouldn't feel that force acting because it acts all over your body. We feel the effects of normal forces on us, and that's how we know what our weight is, by the effect that we feel of normal force. So if I say that in this ride, you're going to feel your weight at the top of the loop, that means that your normal force must be the same size as your weight. That's all it means. This is just like the car question we did yesterday, where I said, you want to feel 4 times your weight when you go through the bottom of that hill. It's the same idea. But to feel your weight means the speed's going to have to be the square root of 2gr. That's how much faster you have to be going. Now, the truth is, roller coasters are far more complicated than this, way more complicated than this. And for those of you who end up going into and you could go into roller coaster design, this is a good state for it, but the state almost always hires outside the state to build their roller coasters. One of the things that you might want to know is that Scorpion doesn't do any of this. Scorpion's actually much different than this. Not in a way that you're thinking. All the rules of physics are the same, but what we're doing wrong is we're thinking of the ride as one car, but the ride is actually a series of cars. When you design a roller coaster, you don't have to worry about one car going through it. You worry about a train going through it, which means that the center of mass never makes it here. The center of mass of the vehicles is lower than the top of the hill. So they don't actually have to be going as fast as what we just calculated. They can be going slower. What's great about that is the trains will still pass through the top, but these cars will be going slower than is necessary to maintain their path through the loop. It saves them energy. I know you guys tend to want to be in this car or in this car. That's where everybody lines up. That's where the extra length of line is. What's funny is the front car is the front car. Everybody loves the front car. Why? It's front. I'm in the front. I'm in the front. It's like when you're little and you want to sit in the front seat. For some reason, it's so much better in the front seat. All that extra leg room. There's all the buttons and knobs. You don't get any of the buttons and knobs in the back. And you can have the aux cord if you're in the front seat. Never get the aux cord in the back seat. But people also line up for the back seat. Now, part of the reason they want the back seat is all of the other cars have gone through the ride first. So they've acquired more kinetic energy. You tend to get whipped around better in the back seat. You experience more G forces in the back seat. What's interesting is in the middle seat, you go the slowest through all the loops, which means you have the best chance of feeling weightless in the middle seat for the loops, just the loops. Because for the other stuff, you want to be in the front or back. Now, I hope that you guys are paying real attention here. Only the Scorpion has a 360 loop like this. None of the others do. And that brings me back to our real discussion here, which is what happens when you don't have enough velocity. If I take all this away for just a minute, just to kind of focus on the car, the single car here. I used to have lots of little toy Hot Wheels stuff. If you focus on the car for just a minute. If you go slower than the minimum, and this side then becomes bigger than the right side, you can't be traveling in a circle. You're no longer traveling in a circle because your horizontal velocity isn't enough to keep you in contact with the track. So you become a projectile. You will fall as a projectile with a parabolic path that's before the circular track. Now that's what happens if you're going too slow and you make it there then. which is why if you look at all of the other rides at Busch Gardens, every single one of them that has an inversion, you will notice that their tracks are all, they can go slower at the top. They don't need as much energy. They need that so that they can actually make many multiple inversions throughout the course of the ride. Because those cars are slowing down. They can't go so fast as to pull too many G's and hurt you, but they still want to have inversions. So you get a bunch of these in the beginning of the ride, and then they start doing the quicker flips later in the ride when the cars have less and less energy. So that's why they do this. It saves them on energy because now this is parabolic. It's not circular. Doesn't cost us as much velocity to stay in contact with the track. Not to mention you ride out here, right? A lot of the dangly ones. When you go through the loop, you're on the outside of the loop. All right. That was the easy one. That was the ease us in. And this next problem is where I got myself in trouble with fourth period. This is where it all came off the rails, so to speak. And wasn't as good. So, oh, come on. It was pathetic. It was not funny. That was terrible. Terrible, Mr. Shelton. You have the worst jokes ever. So here's this is actually from an actual AP question. And I'm bringing it up because, not because it's so terribly hard, but I think you will find it to be challenging. Maybe. We'll see. Perhaps not. So I need to draw this just right. Okay, so we are looking top down on a track. And it's hard to envision this. And I don't have the 3D chops to do what needs to be done here. So I'm gonna try and do this. I want you to imagine what the track looks like. It looks something like this. Okay, so I want you to imagine that if we're looking sideways at it, the track looks like that, except part of it is open. And if we're looking top down, it looks like this 3/4 of a circle. Because what we're going to do is we're going to talk about a box that's going to enter this track with an initial velocity of v0. And it's going to travel along this circular track. So it'd be like right here. Traveling sideways inside the track. Can you imagine that for a moment? I know it's not 100% great, but you get the idea. This is from an actual AP question a couple of years ago. And in that question, there was a small ramp that exited into the circular track. So we're picking up the question here where it's already gone down the ramp and it's entering the circular track. And you can imagine that it will make its way, you know, through the track. So it's going to have a point where it's going to be here. So real quick, and this should be real quick, if everything is frictionless, what is an expression for the normal force from the wall acting on the block? Okay, I want an expression for the normal force from the wall acting on the block. Assume the block has a mass m. That should be a cakewalk. I'm going to wait a minute. But I must hurry because they're going to let you guys out of here in 12 minutes. Now, one of the hard things about this is dealing with forces. These forces are in 3 dimensions. And I know that's going to be tough for some of you. If I look at the block that I've drawn over here, you know, in this part of the track, that's, you know, going right there. Let me expose it a little bit. You know, when we look at this block, it's got, of course, gravity acting downwards. There's a normal force from the ground upwards, but there's also this normal force from the track that's got to be going this way. Normal force from the wall, perhaps. Now, on the actual AP exam, they asked you to draw free body diagrams for this, but they said in this box, draw free body diagrams for the horizontal forces, the one that were acting in the plane of the surface. And then they had another box where they said, draw the vertical forces. So they're very specific on how they wanted that done. The vertical forces are easy. There's just two, weight and and normal from the ground. But we have this normal from the wall, which should have led you to say, okay, net force in the horizontal direction equals m v naught squared over r. The only force that's acting towards the center is this normal force from the wall. This isn't the hard question. You see, this isn't what they had. On the actual question, there was no friction on the floor, but there was a coefficient of kinetic friction between the block and the wall. Now, I want you to think about what that means. Take a few seconds, and I want you to think about all the things that would be affected if there was friction between the wall and the box. And for a few seconds, I'm going to have you guys kind of break up into groups at home, and just 2 rooms. And you guys here in the classroom, break up into groups. You're at your tables, so don't break up into groups, just talk at your tables. Think about all the things that are affected. This is an interesting question. I want you to think it out before we go into the math.
There is no friction between the floor and the wall, right?
That's right, no friction between the floor and the block, like an air trap. And there's friction between the wall and the block. Yeah. That'll make you more comfortable. Yeah. Think about it. What's the friction between the block? Okay, just wrote it down. What happens? Look over there. Normal force equals what? If the normal force changes, what happens to the frictional force? So we have a problem, right? Well, since I kind of gave it away to the whole class, I better give it away to the folks at home. So give me a sec. I gave them 60 seconds, so they're probably still coming back. So I don't want to go too much further into it without getting them back in here, but I'm going to take this and make this a little bit smaller. Or try to. I guess I'm not going to. All right, guys, let's get everybody back. So all of a sudden, we kind of had some conversation in here, and just want to make sure everybody's getting it. First, what does friction do to the block, guys, at home?
Slows it down.
Slows it down. That's exactly it. I'm not trying to ask for, like, we're not trying to make something terribly hard here. The friction's going to slow it down. So if the friction slows it down, what does that do to the normal force?
Reduces it.
And if the normal force is smaller, what happens to the frictional force?
Gets smaller.
So we have a system in which the acceleration is based on the friction. The acceleration slows down the block, which reduces the normal force, which reduces the frictional force, which reduces the acceleration, which is based on the velocity. How would we ever figure out what this object's velocity would look like. Because that would be the next question, actually. On the exam, they wanted you to come up with a motion equation. V as a function of t. And it goes further and asks, how far along the track does it go before it stops? It's a tough question. Very tough question. Now, this is going to push us into some hard math, but I think you guys are good for it. So let's think about how we would take a look at this, because the physics part, the part that involves Newton's laws, isn't that tough. But we do have to now recognize that here, the velocity is not v naught. Here, the velocity is just like v. It starts at v naught and slows down. But at any point in the track, there's going to be a force this way, friction. So to do this problem, what I really want you to think about is we're going to set this direction to be the positive x direction. I want my friction to be negative because I know it's slowing down the block. And this direction is my positive y direction. Now, we already used that because we did that as the horizontal one. That's where we got this normal force relationship. But now we have to deal with friction. And friction is in the x direction. So net force in the x direction equals m-a-t. We have a tangential acceleration. This acceleration slows the block down. This acceleration is changing its direction. Now, this isn't too much. I mean, the only force that's acting in the x direction is this negative friction. So I have an expression for normal force, and I have an expression for friction. If only there was some way to kind of relate the friction to the normal force. If only there was some way. Wouldn't that be nice? Jackson, is there some way we could do that? That's it. That's all we got to do. I'm going to take this and use it here. Kind of out of space here. You mind if I flip to another page? Good, thanks. Appreciate it. So friction is negative m-a-t. Then I have mu k m v squared over r. That's a lot, but that's it. We didn't do anything weird, right? We did all the same stuff we've been doing. Net force in the x, net force in the y, use friction. Create a relationship for the acceleration and the velocity. But here's the rub. The next question says, find a differential equation that would describe the velocity of the block. It's a tough one, isn't it? Yeah. Oh, yeah. But first, we need a differential equation. What do we have to do to get a differential equation? I've told you this. It's one thing. One substitution for all the points. Arushi, do you know what to do?
Could you make a dv dt?
That's it. That's all you have to do. So let's cancel out those m's. I get minus dv dt equals mu k times v squared over r. There, you have created a differential equation. That's it. That was all you had to do. Now, solving the differential equation, that's tough. That's hard. That's what we're going to do right now. I didn't want to do it in fourth period. I tried, and I totally lost everybody. And I didn't get to it in sixth period. We got part way, but then they started complaining about stuff. But here, I think this class can do it. Why? A lot of smarties in the room. And besides, we already talked a little bit about it. We start by separating our derivative, which means multiplying both sides by dt. The next part's really hard. We have to get v to the same side as dv and t to the same side as dt. So I'll do the v part, you do the t part. So I did both parts. Now, this is where you guys are probably done with your math, because the next part is where we have to find, do the integral. And this is the part that's, where I know that you don't know it, but I'm not waiting anymore. Okay, I'm done waiting, because we actually have the rules to do the antiderivative. That's almost all that you need here. So now you're gonna have to grow up, put your big person pants on, and know that when we talk about antiderivative, we start by drawing the integral symbol. This is what we were doing 6 weeks ago. We just didn't do it formally. There are some differences. We're in physics, this isn't calculus. In physics, it's based on the real world. So we know things like the object was at V0 at time 0. We put limits, we put boundaries, we tell our problem things. And we know that it's gonna slow it down so that sometime in the future, it's gonna have some other velocity. We put boundaries on our conditions, on our problems. Now we're smart enough to recognize that constants play no role in this process. So I'm gonna take the constants out, like the -1. Somebody let their kids out early. Ooh. Not too much earlier, I guess. And that leads us to here, which unfortunately, the only thing I gotta tell you is that 1/v² is v to the -2 power. You can do the rest. Don't disappoint me. Bring it to me on Monday. All right, guys, have a fantastic day. Uh-oh, I'm getting a COVID call. That's what my wife and I call them. You guys at home have